Hello, myself Dr. BJD Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss the question bank of Module 5 related to the multiprocessors. The first question is, explain about arithmetic pipelining. So, multiprocessor systems major characteristic is they has to support the concurrent execution of the task. So more than one processor can be employed in the computer and these processors can parallelly execute the task. So this parallelism can be achieved with the help of employing multiple functional units or with the pipelining concept. So the pipelining can be used to overlap execution of the segments of a computational task or the instruction execution cycle. So here two types of pipelining are available. One is arithmetic pipeline, second one is instruction pipeline. So arithmetic pipelines are mostly used in high-speed computers. So the computational capability can be increased with the parallelism to support that the high speed computational or processing can be achieved with the help of arithmetic pipeline. They are used to implement floating point operations, multiplication of fixed point numbers, and similar computationals encountered in scientific problems. So most of the multiprocessor computers can be used for advanced processing applications, and recent technologies in the field of computer science and engineering has to supported with the multiprocessor architectures. So engineering and scientific applications to increase the calculation capability of the computer, the arithmetic pipeline concept can be used. An arithmetic pipeline divides the arithmetic problem into various subproblems, and each task can be executed in a separate segment in parallel with the other segment for a dedicated registers of the processor. So an arithmetic pipeline divides the arithmetic problem into various subproblems for execution in various pipeline segments. So we can discuss the arithmetic pipelining with an example. So here consider two numbers x and y, and which is having x can have the value a into 2 power a, capital B, y have the value b into 2 power b. So for these, the example numbers that can be considered are 0.9504 into 10 cube, 0.8200 into 10 square. So we are considering two numbers whose multisource can be represented with capital A and capital B, and exponents can be represented with small a and small b. So to represent the capital A, capital B, the multisource, the corresponding floating point numbers are considered in the example, and exponents can be represented with small a, small b, and small a is having the value 3, small b is having the value 2. And this is the capital A, capital B, the multisource that are considered in the example. So the combined operation of floating point addition and subtraction is divided into 4 segments. On these numbers, the addition and subtraction algorithm can be applied. So this task can be divided into 4 segments. So in the arithmetic pipeline, the computational task can be divided into small sub operations. So this computational task can be divided into 4 segments. Each segment contains the corresponding sub operation to be performed in the given pipeline. So the sub-operations that are shown in the 4 segments are, the first sub-operation is compare the exponents by subtraction. The exponent values of the two numbers can be compared with the help of subtraction. Second step is align the Montessors. Third step, add or subtract the Montessors. Fourth step, normalize the result. So the computational task of floating point addition subtraction can be divided into 4 sub-operations. In the first step, comparing the exponent with the help of subtraction, align the Montessors, add and subtract the Montessors, normalize the result. These are the 4 sub-operations that are carried out in dedicated segments. What is the first step? So the first step is compare the exponent by subtraction. The exponents are compared by subtracting them to determine their difference. So the larger exponent is chosen as the exponent of the result. So which number is having the larger exponent value, that has to be chosen the exponent of the result. The difference of the exponents, that is, in the example we considered a value, small a value as 3 and small b value as 2. So the difference 3 minus 2 is 1 determines how many times the Montessor associated with the smaller exponent must be shifted to the right. So here the compare the exponent by subtraction so that the larger exponent can be chosen for the exponent of the result. The second step is align the Montessor. The Montessor associated with the smaller exponent is shifted according to the difference of exponents determined in segment 1. So here the Montessors has to be, the smaller exponent is shifted so that the alignment of Montessors can be carried out. So here the first value is having the 10 cube, second exponent is b, small b value is 2. So here by shifting the second value so that the exponents has to be aligned, the Montessors can be aligned. So here b value is 0.8200 to provide the exponent has to be adjusted so that the Montessor can be aligned as 0.082 to the power 10 to the power 3. So in this way, the second step can be used to align the Montessors. The third step is add or subtract the Montessors. The two Montessors are added in the segment 3. So here the exponent value can be the adjusted so that the Montessors has to be added. So the capital A, capital B value that are considered can be added in the third step. Fourth step, normalize the result. After normalization, the result is written into, adjusted into 0.1324 10 power 4. So these are the 4 sub-operations in the floating point addition or subtraction we discussed with a example. Now we will look into the flowchart, how these operations can be carried out. So here, this is consideration of the exponent, small a, small b, and Montessors can be represented with capital A, capital B. So those can be stored in a register. So the first segment 1 is comparing the exponents by subtraction. So here, depending upon the comparison, the difference can be stored and can be used to process the second step, align Montessors. So the second segment has to be align Montessors, choose the exponent. So after that, the third segment can be initiated to add or subtract the Montessors. Next, that result is stored in the register. The fourth step can be the adjust exponent and normalize the result. So this is the step 1. step 2, step 3 and step 4. So these 4 segment operations can be carried out in parallel with other segment so that the speed of processing can be increased with the help of arithmetic pipelining concept. So the next question is, explain the flowchart of 4-segment instruction pipelining with neat sketch. So pipelining is the concept of overlap execution of operational steps of either the arithmetic expression evaluation or the instruction cycle execution. So 2 types of pipelines are available. One is arithmetic pipeline, second one is instruction pipeline. So here the instruction cycle steps, how they can be executed in a overlap fashion to support the parallelism is discussed in the instruction pipeline concept. So an instruction pipeline reads consecutive instructions from memory, while in other segments the previous instructions are being implemented. So pipeline process can occur not only in the data stream but in the instruction stream as well. So one of the major characteristic of multiprocessor computer is it must support MIMD architecture. That is, multiple instruction stream and multiple data stream can be supported. Most of the digital computers with complex instructions require instructions pipeline to carry out operations like fetch, decode, execute the instructions. So each instruction can be executed with the help of instruction cycle, which can generally consisting of 4 steps. So the general steps of instruction cycle are: fetch the instruction from memory, decode the instruction, calculate effective address, fetch operands from memory, execute the instruction, store the result in the proper place. So these are the 6 steps in the instructions cycle, but they are to be reduced so as to implement the increase the throughput and performance of the system. So multiple segments can take a different time duration to work on the incoming data. So this can be avoid instruction pipeline from working at its maximum speed. So to increase the speed for optimal utilization of parallel multiprocessor architecture, the organization of instruction pipeline will be more efficient if the instruction cycle is divided into the segments of equal duration. So one of the most common example for this is the 4-segment instruction pipeline. So the 6 steps of instruction cycle can be reduced into 4-segment instruction pipeline, which is each segment can have the equal duration of time. What are the 4-segment instruction pipeline? A 4-segment instruction pipeline combines 2 or more different segments and makes it as the single one. So here the segment 1 in the 4-segment instruction pipeline is fetch the instruction from memory. Second segment is decode instruction and calculate the effective address. And the third step is fetch the operand from the memory, execute the instruction. So the 6 steps of the instruction, fetch the instruction from memory can be as segment 1. Decoding instruction, calculate effective address can be combined as segment 2. Fetch operands from memory. Third, execute and store the result. Both can be combined as the 4th step. So these 6 steps can be reduced to a 4-segment instruction cycle having the 4 segments. So what are the factors that can influence the instruction pipeline? So the overhead that can be incurred at each stage of the pipeline for data movement buffer to buffer, and the amount of control logic needed to handle the memory and registers. Dependencies can increase with size of the pipeline. It needs time for buffer to operate. So these factors can be considered while constructing the instruction pipeline with 4 segment operations. So what is the operations that can be carried out in each segment can be: in the segment 1, fetch the instruction. The instruction fetch segment can be executed using first in first out buffer. And the second step is decode and calculate the effective address. The instruction fetched from memory is decoded in the second segment, and effective address is evaluated depending on the independent arithmetic circuit. So the second segment in a short can be referred as DA. And segment 3 is fetch the operand, and in short it can be referred as FO. So an operand from memory is fetched in the third segment. Segment 4 is execute the instruction. It can be represented with EX. The instructions are finally implemented in final segment of the pipeline organization. So how the segments of the pipeline can be organized and executed can be illustrated with a flowchart diagram. So the segment 1 is prefetch instruction from the memory. Fetch the instruction from memory. It can be referred as F5. Second one is decode instruction and calculate the effective address. So this step can be referred as DA. After decoding, depending upon the decode value, the type of the instruction can be recognized. So whether it is a branching instruction or a normal instruction. If at all in case of branching instruction, then we have to update the PC value and empty the pipe. So we have to move to the branch location and start executing the instructions at that location. So if it all branch instruction occurs, the PC value can be updated and empty the pipe. If it all it is a normal instruction, the third segment operation, fetch operand from memory, can be carried out. The fourth segment is execute the instruction. At the end of each instruction, the interrupt cycle can be initiated and checked whether any interrupt is occurred or not. If at all any interrupt occurs, interrupt handling interrupt service routine can be executed by updating the PC value, emptying the pipe. If at all not interrupt occur, then next instruction can be fetched. This is the flow of operation of the instruction pipelining process. And the execution and overlap execution of the steps can be illustrated with the timing diagram. So at the each clock pulse, what are the segment operation can be carried out can be pictorially represented with the timing diagram of instruction pipeline. So during the step 1, the instruction 1 can be fetched. This is the instruction 1 first segment. And during second clock cycle, the instruction 1 can be moved to the second segment, decoding and address calculation. At the same time, the second instruction can be moved to initiated and the first step of instruction 2 can be performed, that is the fetch instruction. At the third clock cycle, the instruction 1 moved to the third segment, that is fetching the operand. And next, it has to move, the instruction 2 can be moved to the decode and address calculation, and the third instruction can be initiated and start execution of the segment 1 fetch instruction. So at the third clock cycle, 3 instructions can be parallelly executed. At the fourth cycle, the first instruction execution can be carried out. Second instruction is moved to the third segment, that is fetch the operand. Third instruction is moved to the second segment, decode and address, and instruction 1 is moving to the fetch the instruction. So if you look into the instruction, the steps of each instruction can be executed. Multiple instructions can be carried out at different segments in parallel in the instruction pipeline. So if at all a branch can be occurred, then what happened? It has to update and empty the pipelining. So here, if the branch instruction occurred at this stage, so the next carried out instruction can be, the pipe can be emptied, and the previous instructions that are initiated in the previous clock signals can be carried out in parallel. So what are the pipelining conflicts? So parallelly, the different segment of sub-operations can be executed. Then there exists a conflicts. Those are categorized into three types. One is resource conflict. Second one is data dependency. Third one is branch difficulties. What is the resource conflict? So it is occurred when two segments access the memory at the same time. So same memory location can be accessed with the two segments at the same time, then the conflict can be erased. So it has to resolved by employing separate instruction and data memories so that the conflict can be removed. The second type of conflict is data dependency conflict. Data dependency occurs when an instruction depends on the result of a previous instruction, but that instruction is not available. So the operand access to memory is delayed until required data can be available. So three techniques can be used to resolve the data dependency conflict. One is hardware interlock. So the needed item, the data can be locked so that after utilization it can be available for the next segment. Operand forwarding. The prediction of what operands or data required for the instruction execution, and those can be made available for the process. Next one is delayed load. So as soon as until the availability of required data, the process execution should not be carried out. So it has to wait until availability of the required data. So these are the three techniques. With these, the data dependency conflicts can be resolved. Next one is branch conflicts. So these arises from branch instructions or the instructions that modify the value of PC. Techniques used to resolve these branch difficulties are prefetch target instruction, branch target buffer, loop buffer, branch prediction, delayed branch. So prefetch target instruction, before it's predicting the instruction, and the instruction can be fetched and can be stored so that the branch instruction can be smoothly executed and returned to the main program execution. Next, branch target buffer is the hardware buffer which is used to store the return address from the branch location. Loop buffer is used to delay the shifting to the branch, and the return address can be stored in the buffer. So branch prediction, predicting the branch occurrence, and the location can be stored in the separate buffer in the branch prediction. So delayed branch can be used the same techniques of the delayed operand, so that the required return address has to be stored in the buffer and made available for the sequence execution of the instructions. So these techniques can be used to resolve the branch difficulties. The next question is, define parallel processing and explain the Flynn's classification of computer with a suitable example. So what is parallel processing computer? The parallel processing is used to provide simultaneous data processing tasks for the purpose of increasing computational speed of a computer. So parallel processing system is able to perform concurrent data processing. Parallel processing systems are required to meet the demands of large-scale computations. So, multitasking and multiprocessor systems can be used as the parallel processing. The one of the major characteristic of multiprocessor system is it must support the parallel processing. So, execution of concurrent tasks in the computing process to achieve the faster computational speeds. So, these parallelism can be applied at the job or program level, at the task or procedure level, or inter-instruction level, or intra-instruction level. So, the parallelly the task where a task can be executed. Generally, the amount of work done by the system, that is the instructions, the number of instructions that are executed per a unit of time, generally considered as the throughput. So, if the multiprocessor system supports the parallel computing, more than one instruction can be executed at the same time concurrently, so that the throughput of the system can be increased. So, how this parallel processing can be employed in the system means with the help of multifunctional units. So, parallel processing has high level of complexity that can be achieved by having the multiplicity of the functional units. So, generally, the computer system can have the single functional unit for processing, that is the arithmetic and logical unit. But in multifunctional unit, multiplicity of functional units can be employed for a specialized functions. For example, consider in this diagram here for integer addition and subtraction, adder subtractor is employed, and for integer multiplication, integer multiply, logic operation to perform logic operations, logic unit, to perform shift operation, shift unit, and incrementer. Floating point operations can be supported with the special functional units of floating point adder subtractor, floating point multiply, floating point divide. So, instead of a single arithmetic logic unit, to support parallel processing, specialized multiple functional units can be employed. What are the applications areas where these parallel processing systems can be used? In the expert systems for the artificial intelligence, seismic data analysis, nuclear reactor modeling, visual image processing, VLSI design, aerodynamics, weather forecasting, genetic engineering, and in the defense, these parallel processing systems can be used. What is the Flynn's classification? So, MJ Flynn classifies the multiprocessor systems by the number of instructions and data items that are manipulated simultaneously depending upon the factor of number of instructions and data items. The Flynn classify the multiprocessor computers. The Flynn majorly consider two streams in the instruction execution. One is the instruction stream, the sequence of instructions read from the memory. The second one is data stream, the operations that are performed on the data in the processor. So, depending upon that, four classifications are made by the Flynn. One is SISD, second one is SIMD, third one MISD, fourth one MIMD. SISD means single instruction stream, single data stream. MIMD means single instruction stream, multiple data stream. MISD means multiple instruction stream, single data stream. MIMD means multiple instruction stream and multiple data stream. What is SISD organization? So, it represents a single computer containing the control unit, a processor unit and the memory unit. In this type of architecture, instructions are executed sequentially one after another. Parallel processing can be achieved with the help of pipelining or multiplicity of functional units. The maximum speed of the system is limited by the memory bandwidth. Memory is shared by the CPU and I/O. So this is the architecture of SISD. So here data pool and single instruction pool that are connected to the processor. So here the performance improvement can be done with the multi-programming, spooling and multifunctional processor, and with the pipelining, the performance of the SISD architecture can be improved. The second architecture is SIMD, represents the organization that includes many processing units under the supervision of a common control unit. So all processors receive the same instruction from the control unit and operates on different data items. Shared memory unit must contain multiple modules. So here is the architecture of SIMD. So multiple processing units, they can receive the single instruction pool and can operate on various data pool. The next architecture is MISD, which is not practically used. So here multiple instructions pool can be connected to the processor unit, but single data pool can be connected. Next architecture is MIMD. So MIMD systems capable of processing several programs at the same time. Most of multiprocessor and multitasking systems come under this category. So the architecture of MIMD can involve the processing unit can be connected with multiple instruction stream and multiple data streams. So the comparison of SIMD and MIMD based on the factors of expands to single instruction multiple data is the SIMD, and multiple instruction multiple data is the MIMD, and the memory requirement for SIMD is smaller and MIMD is larger. Programming and debugging is synchronous in the SIMD architecture but asynchronous in MIMD architecture. Number of decoders are single in SIMD, MIMD they are the multiple. Cost can be low in SIMD and medium in MIMD. Performance and complexity, simple architecture and moderate performance. Complex and performs efficiently in case of MIMD. And these SISD, MISD, SIMD, MIMD architectures can be generally used. What are the major characteristics and features of these architectures will be illustrated with this diagram. The SISD can be used in superscalar processors, super pipelined processors, and VLIW processors. MISD are non-existent. SIMD can be used array processors, systolic arrays, and associative processors. MIMD architecture can be used two techniques, shared memory and message passing. In the shared memory, they are bus-based, transfer switch-based, and multi-stage in-based. Message passed techniques can be implemented with hypercube architecture, mesh, and reconfigurable. And what is the nesting of these parallel processing systems are? MIMD is used for optimization of multiple data structures. MISD is parallel computing and is related to the SPU and CPU. SIMD can be used for instruction execution, and SISD is instruction execution with the help of B+ trees. And domain preferences where these architectures can be used is for transaction processing systems, SISD can be used. And for face recognition system, MIMD with shared memory and message passing techniques can be used. 3D graphics rendering, SIMD can be used. Pattern search, design patterns of SIMD can be used. Radar MISD systems and also MIMD systems can be used. Database queries, data processing SIMD can be used. So these are the these architectures where the domain preferences of these parallel processor architectures. Next question is, illustrate number of clock cycles that it takes to process 200 tasks in a 6-segment pipeline. So the number of segments can be denoted with K, and they are the 6 segments. And number of tasks is denoted with N, they are the 200 tasks. The formula for number of clock cycle calculation is K plus N minus 1. So that is 6 plus 200 minus 1. 205 cycles is the solution for this problem. So in this video, I have discussed various question bank problems of module 5 that is based on the multiprocessors. And the references used in this video are textbook of Computer System Architecture by Maurice Manor, Computer Organization and Architecture by William Stalling, and the third one is the web reference. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.